Swayam Prabha. Digital India. Educated India.
So, this class I will solve one numerical example or one example problem related to Tazaki's analysis. So, in the last class I have discussed what is the Tazaki's approach to determine the maximum bending moment or soil bearing pressure for well foundation. So, today I will solve one example problem. So, in the example problem it is given a circular well of external diameter. So, it is given the external diameter d0 is given how much 5 meter, okay, and the depth of embedment is 14 meter below the scour level. So, d is 14 meter because depth is below the scour level. So, that is d. Now, friction angle is given, phi value is given 35 degree and submerged unit weight or gamma dash, that is given 10 kilonewton per meter cube, okay, because here submerged you have to use because water level is or above this soil level. The well is subjected to horizontal force. So, that Q is 1000 kilonewton and the moment is 3500 kilonewton per meter at the scour level. Okay. So, these both are applied at the scour level. Suppose this is the well, so this is your say HFL, this is the scour level and this is the grip length or the depth D, which is 14 meter, this is scour level, okay. This is the HFL and moment is acting at the scour level, okay. So, it is acting or the force is also acting at the scour level. Now, the total net vertical force, so that means the W vertical force is 5000 kilonewton after taking care the buoyancy and the skin friction. Okay. So, that means this buoyancy one is being neglected, skin friction is also taken care. So, total net vertical force which is acting at the base of the well is 5000 kilonewton. Determine the allowable horizontal force, determine the maximum moment in the well with a factor of safety is taken as 2.5. Okay. So, actually horizontal force or the moment is acting here or horizontal force is acting here. So, there is a moment is also acting. So, we can determine what is the H value. So, I can determine what is the H value. So, H value is nothing but this is M by Q. Okay. So, that M is 3500 and Q is 1000. So, this is 3.5 meters. So, now if I apply this moment, suppose this is now the well scour level. Okay. So, this is scour level. Initially, it was applying here the horizontal force. Now, we are applying it here this 1000 kilonewton, but with H value is 3.5. So, that means it is now it is providing a moment of 3500 kilonewton meter. At the same time, the horizontal force 1000 kilonewton is also acting. So, now this is H value is 3.5 meter. Now, this is cover level. This is cover level. It is acting at a height of H, and now this is the grip length D, which is equal to 14 meter. So, now this is the problem. Okay. So, now we know that how we can calculate the D1. D1 is the diameter or the point of rotation from the base of the well, and this is for the light well. So, this is circular light well. So, we can calculate what is this D. D will be 3 by 2, we have taken 2 this side, H1 plus minus half root over 9 H1 square minus 2D 3 H1 minus D. Okay. Now, what is H1 here? So, H1 is equal to H plus D. So, H is 3.5, D is 14 meter. So, this is 17.5 meter. Okay. So, now if I put these values, this is 1.5 into 17.5 plus minus, this is half root over 9 into 17.5 whole square minus 2 into D is 14, then into 3 into 17.5 minus 14. Okay. So, this D1 is 5.77 meter from the base of the oval. So, now it is ranking Ka or Kp or a Kp, or first I am calculating Ka. Say Ka is equal to, or capital A is equal to 1 minus sin phi divided by 1 plus sin phi. This is 1 minus sin 35 degree divided by 1 plus sin 35 degree. So, this is equal to 0.27. So, similarly, we can calculate Kp, which is 1 by Ka, which is 3.7. But remember, this is as per ranking. So, my small q max, which is kilonewton per meter, as for light well equation is given, equation 1 half gamma d Kp minus Ka, then d minus 2 d1. These equation I have already derived. So, this is half gamma dash or gamma sub is 10, d is 14, then Kp is 3.7, Ka is 0.27, then into d is 14 minus 2 into d1 is 5.77. So, this is 590 kilonewton per meter. So, this is 590 kilonewton per meter. Okay. So, now the Q, capital Q max will be how much? Will be 590 into, here it is circular cross section. So, we are taking length is equal to the diameter. So, diameter, external diameter is 5. So, I can write the Q allowable, that will be Q max divided by factor of safety. So, this is 590 into 5 divided by 2.5. So, Q allowable is 1180. So, that means we can allow to apply a horizontal force is 1180, but we have applied 100 kilonewton. So, it is safe, but at the same time there will be a unbalanced horizontal force, and due to that unbalanced horizontal force a moment will develop at the base of the well. Okay. So, that moment is MB, this is due to unbalanced horizontal force or the lateral force. So, that is equal to Q A minus Q into H plus D. So, Q A is 1180 and Q is 1000. So, H is 3.5 and D is 14. So, this is 3150 kilonewton meter. Okay. So, unbalanced force is developed. So, unbalanced due to the unbalanced force there will be a moment. So, that will mean the Q dash max mean that is equal to W A plus M B and Z B. Now, how we can calculate the Z B? So, we are taking the total outside area of the well, okay? Because we are taking total outside area of the well. So, A will be pi d0 square by 4 and pi d0 is 5 meter. So, this d0 is 5 meter. So, this is pi 5 square divided by 4. So, this is 19.63 kilonewton per meter square, and ZB for circular cross section is pi divided by 32. Oh, sorry, this is only meter square. Pi divided by 32 into d to the power q. That is ZB. As I mentioned, I have discussed how I am getting these values. So, for my previous lectures. So, this will be pi 5 to the power cube divided by 32. So, this is 12.3 meter cube. So, here you can say that this is a hollow cross section, okay, but we are taking the outside diameter, because here once the construction is over, then this hollow portion will be filled by the first the bottom portion will be filled, it will be sealed, then it will be filled by the sand or the concrete, then it will be further concreting will be done. So, that means it become a solid kind of structure. Okay. So, that is why we are taking the total outside area, and for Z is also circular cross section. So, that means here finally, I can write that Q dash max mean is equal to W is 6000. What is W? W is W is given, W is given actually 6000. W is taken as 6000, because I have done the calculation by considering W as 6000. So, this is 6000. If it is 5000, you can use 5000, but in my calculation I have done considering 6000. So, that is why I have just done the change. You can put 5000 and you will get the different value. So, that means here I am getting 6000. So, this is 6000 divided by A is 19.63 plus minus MB is 3150 and this is 12.3. So, Q dash max will be 562 kilonewton per meter square and Q dash mean is equal to 50 kilonewton per meter square. So, your Q dash max should not be greater than Q allowable, or this is the allowable bearing pressure, allowable bearing soil pressure, or allowable bearing pressure of the soil. Allowable bearing pressure So, here this allowable bearing pressure of the soil is not given, but if it is given you can check it that whether this is fine or not, otherwise you have to redesign this. Okay. And then again we have to calculate the maximum bending moment. So, for to calculate the maximum bending moment, that we have to determine the x value, and then this x value is for BM max, maximum bending moment, the x is 2qf gamma dash L Kp minus Ka to the power half. Okay. This is x is from the scour level. So, now if I put these values, this is 2, q is 1000, f is 2.5, then gamma dash is 10, L is again 5 which is diameter, then 3.7 minus 0.27, then to the power half. So, this is 5.2 from the scour level. So, the maximum bending moment BM max, that is equal to QH plus 2/3 of x into q. Okay. So, q is 1000, h is 3.5 plus 2/3 into x is 5.4 into 1000. Okay. So, this is 7100 kilonewton per meter. So, this way we can calculate what is the position of the maximum bending moment, which is 5.4 meter below the scour level, and that value is 7100 kilonewton meter. And another thing I want to say, that I have done the calculation by considering 6000, because if I consider the 5000, then your q dash mean will be negative. Okay. So, that also you have to take care. Suppose if it is coming negative, then you have to again redesign, because here I have shown you the example problem. So, it is I have taken the 6000 kilonewton. So, it is coming both are positive, but if you want to avoid that negative stress which is will be generated at the base, then you have to change the dimension. But the dimension you can change in the same way you can do the calculation, and that is same. So, that is why I am not I have done just to considering 6000. So, for your case you can change the design accordingly to avoid the negative stress at the base of the well. Okay. So, this is the Tazaki's approach. So, next one that I will discuss is based on the IRC codal recommendation, IRC 45 1972, that is the elastic theory method. Okay. So, this elastic theory method is applicable for non-cohesive soil, okay, and will not apply if the depth of well below the scour is less than 0.5 times the width of the foundation, okay, in the direction of the lateral force. That means, the direction of the lateral force, if the width of foundation we can calculate, and if the depth of well below the scour level is less than 0.5 times of the width of foundation, then this method is not applicable. Okay. So, but in this method there are different checks we have to do, but I will show you how we can consider those checks. At the same time, I will also show you how these equations are coming, okay, how these conditions are coming. So, these things also been discussed in the code. So, I am explaining those things again here. Okay, suppose if we have a well foundation of this shape, Okay, so this is the well foundation. And this is the scour level. And where H is acting at this level. Suppose H is acting at this level, or I should draw something in different form. So, H is acting here. So, this is the well and this is the center line, and this is the total one is the grip length, which is below the scour depth, or this is the scour level. Fine. So, now this is the width of the well for rectangular cross section. Now, because of this horizontal force H, this well will rotate. So, what is the rotation form? So, the rotation is something like this. Okay, so, rotation will be this is the rotation of this well. Okay. So, that means this is the rotation. Fine. So, that means here once this will rotate. So, what are the forces will developed? So, now I can write this is the scour level, or it will go along this line, and this is the base of the well. Okay, so, there will be original position, then it is rotated. Okay. So, this is the rotated position of the well. So, there will be the rotation or the new position after rotation. Okay. So, this is after rotation, and this is original position. Okay. So, this is deflection profile. So, if I consider a small segment dy at a depth of y from the scour level, and this the amount of rotation is theta. Okay, so, that means the amount of rotation at this point, that will be equal to this r theta. So, what is the r value will be? So, this is y, this is the total one is d. Okay, so, this small arc, this will be r theta. So, r is how much? R will be d minus y into theta, because d is the total one, y is the depth from the scour level. So, from the point of rotation to that small strip, that distance is d minus y. So, total rotation will be or total deflection will be, I should say this rotation is theta and deflection will be r theta. So, r is d minus y into theta. So, this is a small segment and the rotation is also small. So, that means we can consider it is a straight line more or less. And the pressure distribution diagram, because of this rotation there will be a pressure distribution and that pressure distribution is assumed is like this. Okay, so, at that level the stress or the pressure is x dash sigma x. So, this is the pressure distribution diagram. Pressure distribution at the side of the well. So, this is at the side of the well, this is the side of the well. So, where the pressure distribution is like this. So, I can write that from this equation or this figure that the deflection at a depth of y from the scour level will be equal to d minus y into theta. Theta is the amount of rotation. What is theta? Is the amount of rotation. Now, the horizontal soil reaction will be, so now the horizontal soil reaction at that depth that sigma x and that will be equal to k h into d minus y theta into y by d. So, let me explain what is that. So, here k h is the coefficient of horizontal subgrade modulus. Okay, so, that means we know that for the subgrade modulus, if it is P is equal to K into W, if this is the stress, or I should write these things here, that we know that P is equal to K into W, if this is the deflection and this is the stress. Okay, so, that means this is the amount of stress and K is the modulus of subgrade reaction. So, here also K h is the modulus of subgrade reaction and d minus y into theta is the amount of deflection, because amount of deflection. So, deflection into modulus of subgrade reaction or coefficient of horizontal subgrade reaction, or you can say that subgrade reaction, if I multiply that, then I will get the stress. But here the stress distribution is assumed like this, at the top it will be 0 and the bottom also it will be 0. So, that is why this term is added y divided by d. So, now if y is equal to 0, then the stresses will be 0, and if y is equal to d, then also stress will be 0. Okay, so, this is the distribution that is assumed, that is considered. So, that is why this term is introduced. So, now next one is that, so now the sigma x is given as, so we can write that sigma x is equal to m kV divided by d, this is theta, then d minus y into y. So, d minus y into y, theta is there, d is here, kV and m. So, where m is equal to kh minus kV, where kV is vertical coefficient of subgrade reaction. So, I have discussed this vertical subgrade reaction, coefficient of vertical subgrade reaction and the horizontal subgrade reaction during my discussion in shallow foundation as well as the lateral loaded pile. So, this is the kV is the coefficient of vertical subgrade reaction, kh is the coefficient of horizontal subgrade reaction and m is kh by kV. So, that means we can replace kh by m into kV. So, that we have done. So, this is sigma h. Okay. So, now the total soil reaction, this is the sigma x is at any depth which is y from the top from the scoured depth. So, I can write that the total soil reaction that is P, that we have to integrate. So, again if you look at this sigma x whose unit will be, this is kV is kilonewton per meter cube and then y into 1. So, this will be kilonewton per meter. Okay. So, this stress is so this stress is this stress will be this sigma because this is dimensionless. So, this stress, this is now sigma x is equal to kV is kilonewton per meter cube into d. So, this will be kilonewton per meter square. Okay. So, now to make it in, because we are now calculating the force. So, we have to multiply it with the length, then it will give you in terms of, this is now kilonewton per meter. So, in per meter if I convert this one, then this will be sigma x into L. So, then this unit will be kilonewton per meter. Now, what is L? Now, L is, so this L is the cross section of the well. Okay. So, if this is the B and this is the L. Now, when we are looking this well in the from the front, so this is the front side. So, we are looking this from this side, okay, and this is the view where this is the width. So, and the perpendicular to this figure. So, this is the length of the well. So, that we have to multiply with sigma x. So, then it will give you kilonewton per meter, and that we have to integrate along the length or the depth of the well, then you will get the total soil reaction. Clear? First we are getting sigma x, which is kilonewton per meter square, we multiply it with the length. So, that will give you the kilonewton per meter, but we have to calculate in terms of kilonewton, then we have to integrate it along the total depth of the well. So, that we are doing here. So, that means we are integrating it 0 to d, because d is the total depth of the well, and then L and sigma x, and that is dy. Okay. So, now we can get from here that P is equal to, so if I now put 0 to d L and sigma x value is m kV divided by d theta d minus 1 y into dy. Okay. And finally, we can take that m kV divided by this is that is the L term. So, this is kV theta. So, there is a m kV theta, then L divided by d, then we put the integration 0 to d, then this is y d minus y square into dy. So, y d minus y square into dy. So, finally, after integration 0 to d y d y square minus dy, after integration we will get that P is equal to m kV into theta L divided by d, and after integration putting the limit of 0 to d, we will get d cube by 6. Okay. So, now I can write that I v is equal to L d cube by 12. So, which is the moment of inertia? So, about the horizontal axis. So, now I can convert P is equal to, this is 12. So, this will be 2 m kV into theta. So, theta, and this is L d cube by 12. So, that is why this is 2. So, this will be I v, and then the total is d. Okay, 2 m kV theta I v divided by d. Yes. So, this is the total force or total soil reaction. So, that means this is the total horizontal soil reaction. So, that total horizontal soil reaction will act where? So, now it will act here. So, this is the total horizontal soil reaction that is acting here, because now this is the total stress distribution. Now, P is the total force, and this force is acting here. So, because of this force, and there will be friction or shearing will occur along the depth of the well. I mean, that friction is between the soil and the wall, or the soil and the well. So, that we can write as mu dash into P. So, P force is acting, and there will be a friction between the soil and the wall of the well. So, that is mu into P, mu dash into P. So, where mu dash we can write as coefficient of friction between the soil and the side wall. Okay. So, I can write here. Okay. So, later on I will write there. So, in the so that means in this class we have determined the total soil force. Okay. So, horizontal soil or the total horizontal force due to the soil reaction, because the well is rotating, and then when it is rotating, the soil will give the reaction. So, that total reaction force of the soil is P, and that P we have determined, and because of that P there will be a friction between the, and there will be a friction between the soil and the side wall, and that friction is P into mu dash. So, next class I will discuss that here. Now, the side wall soil reaction we have determined, but there will be a soil reaction from the base of the well also. So, that also I will determine, we have to determine. So, that I will determine in the next class. Thank you.